Look closely, this stick figure is called Xylene. We can also affectionately call him Xiao Cheng. As everyone knows, mathematics is the foundation of physics for studying the world. After clearing the math realm in the last episode, Xiao Cheng, with super learning ability and physical fitness, began his adventure in the world of physics. Xiao Cheng's entrance is an elegant free fall. As Xiao Cheng walks, he first discovers an important concept in physics: distance. Then he discovers the concept of speed. Speed is represented by direction and magnitude. Speed equals distance divided by time. He discovers displacement. Displacement is a directed line segment from the initial to the final position. It's independent of the path. Total displacement divided by total time gives average velocity. So Xiao Cheng starts to experience speed and passion. Xiao Cheng keeps accelerating. He falls flat on his face. Xiao Cheng is really very smart. With a little probing, he discovers mass, acceleration, and force. The relationship between these three physical quantities, that is the famous Newton's second law. Force is the reason an object gains acceleration. When a force displaces an object, it does work. Work done per unit time is power. Projectile motion, an inelastic collision in projectile motion. Part of the mechanical energy is lost and converted into internal energy. Coefficient of friction. Here we can see, the friction coefficient of the white ground on the left is 0.5. That's about the anti-slip level of ordinary tiles. The black ground is 0.1. That's about the level of an ice surface. Xiao Cheng has good balance. He does an impromptu breakdance on the ice. The force analysis on his feet isn't very rigorous. Just treat it as a visual effect. Since he's not wearing shoes, Xiao Cheng can barely move on the ice with its extremely low friction. Suddenly, a rope falls from the sky. It startles Xiao Cheng. Xiao Cheng looks at the mysterious star again. Here, because Xiao Cheng has a large mass, and the ice surface isn't perfectly smooth, according to the friction calculation formula, to get Xiao Cheng moving, at least 50 newtons of force are needed. So Xiao Cheng doesn't move while pulling the small ball. Angular momentum. Xiao Cheng discovers another important physical quantity. Angular momentum equals momentum times radius. Woo 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 woo. Entering the hole. This is a very magical effect related to angular momentum. A rotating object generates angular momentum. Angular momentum is the product of momentum and the radius vector. Its direction follows the right-hand screw rule, and torque changes the direction of angular momentum. The torque generated by gravity also follows the right-hand screw rule. Its direction is perpendicular to the angular momentum direction. So the wheel starts spinning. The most common application is the gyroscope. So at this moment, Xiao Cheng becomes a human gyroscope. He spins happily on the ice. Conservation of momentum. Xiao Cheng uses the ball's momentum to fling himself away. Note, this is very interesting. If the ice surface were perfectly smooth, then Xiao Cheng and the ball, as a whole, horizontally, could never move. But because there is a bit of friction here, when throwing the ball, Xiao Cheng, using the ice's friction, doesn't move. Then, at the moment the ball flies out, he jumps slightly. This avoids ground friction, thus completing this slick move. This actually embodies a very basic law in physics. In the absence of any external force, an object will remain at rest or in uniform linear motion. This law, which seems incredibly simple now, actually went through a long history. Initially, the Greek philosopher Aristotle wrote in his Mechanics, when the force pushing an object stops pushing it, the object returns to rest. Later, Galileo discovered that if the ground were perfectly smooth, the object wouldn't stop. Later, Newton wrote this law as Newton's first law. Of course, there is still a bit of friction on the ice here, so Xiao Cheng will actually slow down gradually. Classic potential energy conversion slope. This slope can be seen everywhere, in classical mechanics, quantum mechanics, cosmic explosion models, and various energy conversion places. The color gradient represents the energy conversion process. Xiao Chang hesitates here for a moment, causing a loss of kinetic energy. This prevents him from reaching the top of the opposite side. Xiao Chang immediately thinks of using the pull of a tree branch to add an initial forward kinetic energy. Thanks for the rocket, bro, and thanks everyone for the one-click triple support. Xiao Chang climbs up the tall tree. Torque. Torque is defined as the cross product of the radius and force vectors. Since force equals mass times acceleration, torque is actually the derivative of angular momentum. With respect to time, it changes an object's angular momentum. Xiao Chang thinks of another slick move. Whoosh, lift off. At this moment, Xiao Chang turns into a beam of light flying into the sky. Xiao Chang's speed is very high enough to let him fly into space. So where did his speed come from? From the perspective of conservation of angular momentum, it's because when r gradually becomes smaller, v becomes very large. And from the perspective of conservation of energy, it's simpler. Most of the gravitational potential energy sacrificed by the white ball below is converted into Xiao Chang's kinetic energy, along with some internal energy from tree friction. Notice, Xiao Chang's gravitational acceleration keeps decreasing until it reaches 0. Xiao Chang arrives at an idealized, completely weightless space environment. This rocket seems to be sound-controlled or pressure-controlled. Xiao Chang kicks his legs. The rocket starts accelerating. Thrust. The rocket's recoil is also part of momentum conservation. The mass of fuel expelled per unit time times its velocity is the rocket's reaction thrust. He runs head-on into a cowboy hat. This hat will be useful later, but I don't know what the 5-pointed star on it symbolizes. If you know, feel free to tell me. You can pot it in the comments or bullet comments. Special relativity. Those who have watched my relativity series videos should be very familiar with this. This gamma is the Lorentz factor. It is the essence of special relativity. All corrections special relativity makes to classical mechanics basically involve this Lorentz factor. Meaning, as speed approaches the speed of light, relativistic effects become more and more obvious. You can see, compared to the speed of light, Xiao Chang's speed is still very low. There are two pieces of information here. One is that Xiao Chang discovers light travels in straight lines. The other is that Xiao Chang's head is hollow. Here you can see that even though the rocket keeps accelerating, the value of the speed of light remains constant. Light still exists behind the hand blocking it, so Xiao Chang discovers that light has wave properties. Xiao Chang discovers that by adjusting the wavelength of light, he can change its color. At this moment, a star system suddenly appears ahead. Xiao Chang is startled by a planet that suddenly pops up. He quickly accelerates to avoid a collision. He accidentally completes a gravitational slingshot effect. Xiao Chang finds the acceleration effect of this slingshot amazing. Tasting success, he decides to do it again. Xiao Chang rushes straight towards the star. Judging by its color, this star should be a red dwarf. Xiao Chang realizes something is wrong. He immediately turns around, trying to escape its gravitational field, but finds the rocket's thrust isn't enough to escape. So he simply accelerates directly along the velocity direction. Finally exceeding the star system's escape velocity, he successfully escapes. After Xiao Chang's fierce series of moves, his speed finally reaches 1% of the speed of light. An unknown magnet appears ahead. Xiao Chang discovers the laws of electromagnetism. On the way to the mysterious star, a series of giant magnetic rings appear. Xiao Chang has a brainwave. He thinks of another slick move. He first uses a magnet to magnetize the entire steel pipe. Then he uses his astonishing arm strength, honed over 20 years single. He bends the steel pipe into a solenoid with his bare hands. This is a small solenoid with only 2 turns. At this point, Xiao Chang is like a small magnet. Xiao Chang arrives in front of the giant magnetic ring. He plans to use it to accelerate again. You can see that Xiao Chang goes directly from 1% of the speed of light to 80% of the speed of light. It's clear that this electromagnetic ring's acceleration effect is very good. As a supplement, this electromagnetic ring is actually the acceleration principle of a real-life railgun, except in actual operation. When the object passes through the center of the magnetic ring, the magnetic field is turned off or reversed. The animation doesn't show this point, but it doesn't affect our continued viewing. Note, at this point, Xiao Chang's relativistic effects are already very obvious because the speed is too high. The light in front and behind undergoes blue shift and red shift respectively. This is because the Doppler effect of light is the same as for sound waves. When moving towards the wave source, the received wave frequency becomes higher. Conversely, it becomes lower. And when the frequency of light increases, it manifests as the light's color shifting towards the blue end. Hubble, based on the light emitted by distant galaxies, all showing red shift, discovered that the universe is expanding. Time dilation, also called the clock-slowing effect. This is the first important effect of special relativity. The coordinate system here is actually the Lorentz transformation of spacetime coordinates. Its geometric principle won't be detailed here. You just need to know that when an object moves relative to us, you will see its time slow down. Length contraction. The second important effect of special relativity. When an object moves relative to us, its space is compressed in the direction of motion. You will see its length become shorter. Note, these are real changes in spacetime, not visual effects. You can see that Xiao Chang comes from a spiral galaxy. He is preparing to head towards a quasar. Our Milky Way is a spiral galaxy, but because it has a not-so-obvious bar structure, the Milky Way is classified as sab-type. Obviously, Xiao Chang is not from the Milky Way. A quasar, as the name implies, is a celestial body similar to a star. In fact, it is a galactic nucleus. It is one of the brightest objects in the universe. Its center is usually also a supermassive black hole. Gas and dust around the black hole are attracted and accumulated by gravity, forming an accretion disk. Due to the black hole's powerful gravity, matter near the black hole is accelerated to near light speed. Combined with the action of a strong magnetic field, high-energy particles and radiation are emitted, forming jets. They are ejected along the black hole's axis to extremely far distances. As Xiao Chang gets closer to the black hole, the frequency of light he receives gets higher and higher. Riding with the swift wind, a meteor trails behind him. Here we can see that Xiao Chang's physical fitness is indeed very good. He swims upstream against the gamma rays. Xiao Chang whooshes right through the accretion disk. Leveraging the black hole's powerful gravity, Xiao Chang reaches 99% of the speed of light. Using Xiao Chang's perspective, let's get to know the black hole properly. You can see the shape of this black hole is very similar to the black hole in the Mu-6 Interstellar. In fact, the appearance of the black hole in Interstellar is indeed the most accurate black hole model ever made. This is the accretion disk formed by various materials rotating at high speed. This part of the accretion disk is actually behind the black hole, but because light is bent by the black hole, you see this kind of visual effect. This is the event horizon. Its radius is called the Schwarzschild radius. You can simply understand it as the escape velocity here reaches the speed of light, so even light cannot escape. A more profound way to put it is that all light cones here are distorted and deformed. Spacetime flips. Your world line points towards the future singularity, so falling into the black hole and crashing into the singularity will be your only fate. And outside the event horizon, there is also a faint ring of photons. This photon ring is actually the effect of photons that happen to pass by here being bent by gravity. Some photons may need to orbit many times before they can escape, then shoot into your eyes, allowing you to see them. Let's continue watching. That mysterious star appears again. Without a word, Xiao Chang, with excellent mental and physical qualities, heads straight for the black hole. There is a very important detail here. From an external perspective, Xiao Chang gradually slows down as he approaches the black hole until he stops moving. This is actually the time dilation effect caused by the gravitational red shift in general relativity. The stronger the gravitational field, the slower the time. Cooper, the protagonist of Interstellar, after finishing his mission near the Gargantua black hole, found that his companion on the spaceship had aged decades. This is the same principle. The closer you get to the event horizon, the slower time passes from an external perspective until it completely stops. So the black hole also has a name, frozen star. Except it doesn't freeze objects, it freezes time. But from his own perspective, time doesn't change at all. Xiao Chang's passage through the event horizon is smooth and continuous. So, looking back, Xiao Chang would see the outside world, time flying by, a moment seeing 10,000 years. He could even see the end of the universe. Because the light is severely bent, the external field of view gradually shrinks. At the same time, because Xiao Chang's speed is increasing, the light coming from outside is redshifted more and more severely until it completely disappears. Spaghettification. Inside the black hole, because spacetime is curved too severely, the difference in the speed at which the space at his feet and head is dragged by the black hole is large enough to tear his body into a long strip. Of course, you can also simply understand it as a tidal force difference. But no big deal. Our Xiao Chang's body resilience is also excellent. Stretching is healthier. Another important piece of information appears here. This black hole has two event horizons, an outer event horizon and an inner event horizon. This indicates it is a Kerr black hole. The black holes we usually discuss are Schwarzschild black holes. They are an idealized, non-rotating black hole. The so-called singularity theorem was jointly proposed by Penrose and Hawking for Schwarzschild black holes. But in reality, black holes should all have spin. This Kerr black hole. A Kerr black hole has two event horizons. The outer event horizon is the same as that of a Schwarzschild black hole. Once inside, no object can escape the black hole's gravity. And at the center of the inner event horizon, there is also something similar to the singularity of a Schwarzschild black hole called a ring singularity. This is a ring full of quantum effects. It lies quietly on the black hole's equatorial plane. This information is crucial for understanding Xiao Chang's subsequent experiences. Due to the spacetime curvature of general relativity, space here contracts rapidly towards the ring singularity. Xiao Chang's body is also compressed and becomes smaller. But no big deal. Xiao Chang still looks full of energy. Here, he enters the atomic realm. This is the electron orbital probability tau of a hydrogen atom. You can see its three quantum numbers are 211, representing the energy level, angular momentum quantum number, and magnetic quantum number. The actual distribution pattern of hydrogen atom orbitals solved from the Schrödinger equation. You can see the diagram in the animation is quite rigorous. A hydrogen nucleus has only one proton. The nucleus diameter is only about 1/10,000 to 1/100,000 of the atom's diameter. A proton is composed of two up quarks and one down quark. The lines in between are the strong interaction binding them together. At this moment, a photon hits one of the quarks and excites a pair of quark-antiquark. Now Xiao Chang sees neutrinos, known as ghost particles, and passes through various string world sheets with them. Just as a world line describes an object's motion in spacetime, a string world sheet describes the vibration pattern of a string. Here, Xiao Chang suddenly arrives at a place called anti-de Sitter space. The so-called anti-de Sitter space is simply the opposite of de Sitter space. We know general relativity says our spacetime can be curved. So what is the shape of the entire universe? Thus, de Sitter proposed de Sitter space back in 1917. It is a solution to Einstein's field equations for a universe with positive spatial curvature. Solution. So, anti-de Sitter space means a universe with negative spatial curvature. Note, current cosmological observational data and theoretical models support our universe being a flat universe with near-zero curvature. So Xiao Chang should have come to another world here. And this so-called conformal field theory is actually a type of quantum field theory, except it assumes conformal symmetry, meaning scale invariance. That is, spacetime is completely flat. Later, someone discovered that this anti-de Sitter space from general relativity and this conformal field theory from quantum theory have a high degree of duality. That is, both can be described using the same mathematical method. This duality relationship is crucial for studying black hole thermodynamics, and it provides a new perspective for understanding the relationship between gravity and quantum theory. According to this duality, physicists speculate that our spacetime itself emerges from quantum phenomena, and we shouldn't try to explain spacetime using quantum methods. At the same time, it also allowed physicists to discover a new method for theoretically constructing wormholes. At this point, Xiao Chang is gradually approaching the Planck length. Note, a Penrose diagram appears in the bottom right corner, also called a spacetime diagram. This is a special spacetime diagram that uses finite coordinates to represent infinite spacetime. The horizontal axis is time. The vertical axis is space. The horizontal wavy lines at the top and bottom represent the future singularity and past singularity, respectively. Meaning they cut off all world lines leading to the future and past. That is, any object falling within the horizon will inevitably hit the singularity. But the direction of movement of the orange dot here is moving away from the singularity. So there is a problem with the animation here. And this diagram describes a non-rotating Schwarzschild black hole. But our Xiao Cheng entered a rotating Kerr black hole. The Penrose diagram for a Kerr black hole looks relatively more complex. In fact, if falling into a Kerr black hole, Xiao Cheng's path should be first pass through the outer event horizon. Then, the space falling speed here exceeds the speed of light. Space-time swaps roles. If it were a regular Schwarzschild black hole, Xiao Cheng would have been crushed by the singularity long ago. But due to the rotation of the Kerr black hole, the outward pressure on space gradually exceeds the inward flow speed caused by gravity. Eventually, the space flow slows down to less than the speed of light. This creates the second event horizon, which is the inner event horizon. After entering the inner event horizon, space-time swaps back to the correct order. At this point, Xiao Cheng is no longer falling endlessly. He can freely explore the black hole. For example, choose to go back the way he came, or jump into the ring's singularity. Here, Xiao Cheng sees another Xiao Cheng. You can see that this ring singularity's location is a place full of quantum characteristics. The moment Xiao Cheng lands, he triggers a probability wave. In quantum mechanics, the square of the absolute value of the wave function represents the probability of a particle appearing at a certain location. The formula below is the kinetic energy plus potential energy from the Schrödinger equation. Here, pairs of particles and antiparticles constantly appear and disappear out of nothing. Calabi-Yau manifold. This is a type of six-dimensional space in mathematics. Superstring theory posits that the spacetime of our universe actually has 10 dimensions. We can only perceive four-dimensional spacetime in our daily lives because the other 6 spatial dimensions are curled up within this very small Calabi-Yau manifold. And Xiao Cheng has now shrunk to a very small scale, so he can perceive dimensions that we in the macroscopic world cannot. Xiao Cheng finally arrives at the black hole's ring singularity. You can see this ring singularity is not simple. On it is a polyhedral projection of a hyperbolic space. As mentioned before, anti-de Sitter space is a spacetime with negative curvature. And hyperbolic space is also a geometric space with negative curvature. So we can understand it as, this is the projection of the entire anti-de Sitter space onto the ring singularity. At the same time, the duality of anti-de Sitter space and conformal field theory shows that a gravitational system in anti-de Sitter space can be equivalently described as a conformal field theory on its boundary. That is to say, we can encode the information of a higher dimensional physical system into a lower dimensional system on its boundary, just like a holographic image. At the same time, this ring singularity is also an Einstein-Rosen bridge, which is what we commonly call a wormhole. A wormhole connects two worlds. So, combining the characteristics of wormholes and high-dimensional projections, you will see a series of slick moves by Xiao Cheng later. Xiao Cheng sits down. His energy excites an open string. In string theory, all elementary particles are generated based on different vibration modes of strings. And strings are divided into open strings and closed strings. They can transform into each other. This open string in Xiao Cheng's hand transforms into a B string through collision. Xiao Cheng throws this open string into the ring singularity. It projects a rope. It is transmitted through the wormhole to his counterpart in another parallel universe. The Xiao Cheng on the left pats the ground again with his hand, exciting an open string and a closed string. This time, the Xiao Cheng on the right throws the closed string into the ring singularity. This time, it projects a heavy ball. This part is very interesting. We know that in string theory, closed strings are related to gravity, and the heavy ball represents gravity. This symbolism is quite clever. Xiao Cheng handcrafts a Schrödinger's rocket. Tipler cylinder. This is an obscure time machine hypothesis proposed by American physicist Frank Tipler in 1974. Its principle is, if there is an infinitely long cylinder with enormous mass and density, after it starts rotating, it will produce a severe frame-dragging effect on the surrounding spacetime. By moving along a suitable path, we could travel back in time. There is also another interesting sheet to read. Once, someone appeared online claiming to be a time traveler from the future. Unlike other time travelers,